Thank you, Clay. Thank you, Kendra. It's just to build on what Clay said. We have just an hour to cover a technology that when I was with Union Carbide, I was part of a team that spent 6 weeks, uh, training new salespeople and new technology people in the use of molecular sieve adsorbents. And we're going to try to condense that into 1 hour. So there probably are going to be a lot of questions that you folks have. What we're going to discuss today is to explain how an adsorbent works. We're going to look at the different types of molecular sieves that are commercially available. Today's session focuses exclusively on molecular sieves. We will also take a look at a typical cycle of an adsorption unit, that is the adsorption cycle and regeneration cycle. The cycles we will be discussing are thermal swing adsorption cycles, where we use temperature to regenerate. We are not going to be discussing pressure swing cycles, which is generally not used for purification in the natural gas industry. And finally, we will take a look at the reasons, the key reasons why dehydrator units may not be performing properly. So let's start with how an adsorbent unit works. First, the definitions. Absorption with a B is the affinity for a molecule to go into the liquid phase. Typical absorption units are TEG, triethylene glycol units, and amine units. Adsorption with a D is the affinity for molecules to adhere to the surface of a solid. That's what we're going to be focusing on today. The adsorbent is the solid that is holding the molecule onto its surface. The adsorbent we will be discussing is molecular sieves. And the adsorbate is the molecule that you want to remove from your carrier stream. We're going to focus primarily on water as the adsorbate. There are numerous methods for dehydrating natural gas. You can see the different approaches or different technologies on the screen. You'll notice that the molecular sieves is the only technology that can get you down to less than 1/10 of a part per million by volume. As a consequence, molecular sieves are used primarily to remove water from any downstream cryogenic units, such as LNG plants and turbo expander plants. The capital cost of a molecular sieve unit compared to TEG units it's considerably higher capital cost, and there's also a higher energy consumption per pound of water removed when using a molecular sieve unit. Consequently, you will tend to use mole sieve units only when you have to get to very, very low water dew points at the outlet. The solid adsorbents, the molecular sieves that we're going to be talking about, they're very porous solids with huge surface areas. The surface area is on the inside of the pellet or the bead. There's lots of channels and a high amount of surface area within the structure of the molecular sieve. What happens is that an impurity, such as water, enters the pore of the adsorbent, the molecular sieve, and is held tightly onto the surface inside the cavity. When heated or when the pressure is reduced, the impurity is released, and that is how the molecular sieves are regenerated. As I mentioned before, we're going to focus on thermal swing adsorption, where you absorb at a generally high pressure and low temperature, and you regenerate at low pressure and high temperature. There are many cases where we also regenerate at high pressure and high temperature, and we can get into that a little later if you desire. Pictures of a molecular sieve unit. I love this picture. It is an old picture. You can see this guy here has no proper PPE. Molecular sieves have been used for at least 50 years, probably more. This shows a 3-vessel adsorption system. Here we have 4 trains. Each train consists of 3 vessels. And here we have 1 train consisting of 4 vessels. You'll notice in this, which is particularly interesting, that the L/D ratio seems to be rather smaller than one might expect. Sieves can work with small L/D ratios. What do they look like? Well, they come either in beads or in pellets. Generally, the size, the size of the material for pellets, they range from 1/8 of an inch or 3 millimeters in diameter, and the other size is 1/16 of an inch diameter or 1.5 millimeters. The beads are generally sold as a mesh cut. They're either 4 by 8 beads, which is a larger bead, equivalent to 1/8 of an inch in diameter, and the 8 by 12 cut, which is equivalent to 1/16 of an inch or 1.5 millimeters in diameter. So that's essentially what they look like. Let's take a little harder look at what they actually are. This is a mouthful. The alkaline metal crystalline aluminosilicates. What that means is that the crystalline means that it has a very ordered structure, and the structure consists of alumina, silica, and oxygen. And to balance out the negative charge, you'll have to add an alkaline metal such as potassium, sodium, or calcium. The result, when you mix all this stuff together, is that you end up with a material, a molecular sieve material, that has very precise pore openings. And in addition to having precise pore openings, because of the distribution of the ions, you also have a highly polar particle where one side is negatively charged and the other side is positively charged. Because of the precise pore openings, you have these types of sieves that are commercially available, type 3A, 4A, 5A, and 13X, and they all have very precise pore openings. They have an affinity for polar molecules because of the distribution of the positive and negative charges on the molecular sieve particle itself. And the things that affect adsorptivity of any molecule are its polarity, the nominal diameter, the nominal molecular diameter of the species you're trying to adsorb. Remember, that species, such as water, has to fit into the pore opening, and if it's polar, then it's going to attach itself very readily onto the surface of the molecular sieve. Some molecules, such as water, are very strongly held onto molecular sieves, and other molecules are very weakly adsorbed onto molecular sieves, such as CO2 or even hydrogen sulfide. As a consequence, we're going to see that the strong species can displace the weak species during an adsorption cycle. This is what they look like. It's crystalline in nature, and you have a whole bunch of truncated octahedra that are attached to other octahedra, either on a 4-sided figure or a 6-sided figure. The bottom line is that you end up creating very precise pore openings into this type A molecular sieve or into this type X molecular sieve. As we mentioned before, they're available as beads or as pellets. So let's take a look at what an adsorption process consists of. You have an equilibrium zone. The equilibrium zone is that portion of the bed that is fully loaded with water. It cannot handle any additional water, so you've reached equilibrium. You have a mass transfer zone, and the reason for the mass transfer zone is that the water will not find its way into the internal pores immediately. It goes through some resistances, and it takes time for that water to find its way onto the surface of the interior pore structure. And then finally, because of the cyclical nature of the process, you have an active zone. And as your cycle time continues, as you continue to go from 1 hour to 3 hours to 8 hours of adsorption, your active zone is going to shrink as your equilibrium zone moves further down the bed and your hopefully stable mass transfer zone continues to move down the bed as well. You're always going to have some active zone that will allow you to achieve the lifetime that you want the sieve to achieve. Typical lifetimes range anywhere from 3 to 5 years. Let's talk now about the equilibrium zone. We'll then talk after that about the mass transfer zone and finally the active zone. To determine the section of the bed that is required for the equilibrium zone, we use isotherms. And isotherms are a plot of water loading, or the percent of water that is held onto molecular sieves. In this FPS slide, it's pounds of water held per 100 pounds of molecular sieve. And it's plotted versus the partial pressure of water in the gas phase. And we have lines of constant temperature varying from very cool temperatures to very hot temperatures. Let's see how this works. If you take a feed stream that has coming in at a pressure of 900 pounds, a temperature of 86 degrees, and is water saturated, and you can convert the water saturation to a partial pressure, and knowing this relationship of the mole fraction of the water as being equal to the partial pressure divided by the total pressure, you can figure out what's going on with the isotherms with this example, with this particular example. You come in at the 0.8 psi, you go up to your adsorption temperature of 86 degrees, and you find an equilibrium loading of 23.5 weight percent. That means that when the molecular sieve is brand new, it can hold a maximum of 23.5 weight percent of water. Now, we want to get rid of the water, so what we're going to do is we're going to use, in this example, product gas to regenerate the water. And we're going to take that clean, bone-dry product gas at 500 degrees Fahrenheit, and we're going to regenerate it. You're going to see that you'll have a partial pressure here of on the order of 3 times 10 to the minus 7, which is going to give you a theoretical water dew point of 3 parts per billion. That's parts per billion by volume. That's the theoretical water dew point. When you receive a quote from a vendor, typically the vendor is going to quote, "I'll warrant that the outlet will be less than 1/10 of a part per million by volume." That's because that's the best that the vendor can measure. When you regenerate a bed, here we have a bed that's standing vertically, and we adsorb down, and we regenerated, we heat and cooled up. The result of this is that we are never going to get rid of 100% of the water from the bed. And you're going to have this profile, which is the residual water that is left in the vessel after the regeneration. There's very, very little residual water at the product outlet and more residual water at the top of the bed when you heat and cool with product gas in the upflow direction. So your net loading, your net equilibrium loading that you can actually use in order to determine what the equilibrium section will look like is equal to the loading that you get from the isotherm minus this residual loading. And as an average residual loading, you can assume 4 weight% as a good number. So that means that 23.5 minus 4 will give you a net loading of 19.5 weight%. But that's when the molecular sieve is brand new. As the molecular sieve ages, that loading is going to decrease. We'll talk about that in a few moments. We just reviewed the equilibrium section. Let's take a look at the mass transfer section. Here we have a bed that shows the equilibrium zone, the mass transfer zone, and the active zone. And I have a plot of the outlet water concentration. This is on the outlet of the vessel versus time. And we show 3 breakthrough curves. Theta BT is the water breakthrough on 3 different situations. Let's look at the time at this point in time, and we'll take a look at the green curve. The green curve shows what would happen if you have no mass transfer zone. In that case, this entire section, because I have no mass transfer zone, is an active zone. So you have a lot of material that is available for absorption when you have no mass transfer zone. If you look at the blue curve is what's shown in this diagram over here, where you have an equilibrium zone, a mass transfer zone that is already formed, and an active zone that is going to move down the bed as the cycle continues. Looking at the red curve, where you have an abnormally long mass transfer zone, what happens is for the same cycle time, this entire section here is mass transfer zone. You have no active zone. That means with a very long mass transfer zone, you're only going to be able to run to this cycle time before you see water breakthrough. With no mass transfer zone, you can increase the cycle time, at least in this picture, by 2 to 3 times. Typically, where you're looking at the blue curve, that shape of a mass transfer zone. So, what affects the length of the mass transfer zone? We know we want small mass transfer zones. Well, probably the biggest thing that will affect you is contaminants in the feed gas. I'm going to say this many times during this presentation. Invest in a good quality inlet filter coalescer. You will do well by having a good inlet filter coalescer. Not having one, you're going to be chasing your tail, and you're going to have a lot of difficulty in dealing with the unit. When I was involved with the Field Technical Service Group at Union Carbide, which I managed for a few years, 80% of my troubleshooting was traced down to a poorly performing inlet filter coalescer. So keep contaminants out. The contaminants coat the surface of the molecular sieve, and what it does is it ends up increasing the resistance to the mass transfer. The second thing that will affect your mass transfer is the size of the desiccant. Remember, we said they come in either 3 millimeter diameter or 1.5 millimeter diameter. the larger the desiccant size, the bigger the mass transfer zone. Well, great. Why don't I then use smaller diameter pellets or beads in all my units? If you did that, your pressure drop would go up. So there's a balance between the size of the mass transfer zone and the pressure drop. Most units in natural gas dehydration tend to use 1/8 or 3 millimeter diameter pellets or 4x8 beads. The next thing that affects the size of the mass transfer zone is the gas flow rate. The higher the flow rate, the higher the mass transfer zone. And finally, we have aging. Aging, you're going to get because of the cyclical nature of a thermal swing process, where you are where you're impacting the molecular sieves from temperatures of maybe 86 degrees Fahrenheit, 30 degrees Celsius, up to 550 degrees Fahrenheit, 288 degrees Celsius, you're going to see a lot of hydrothermal damaging of the molecular sieves. This is normal. In addition to the constant heating and cooling of the sieves, we also have contaminants that will adversely affect the aging. And you take all this into account, and it will affect the size of the mass transfer zone. So when we combine all this, what we end up with is a molecular sieve capacity decay curve. This is a plot of the life factor of an adsorbent versus the number of cycles. This is not time over here, it's the number of cycles. And if you look at this, you can conclude that the longer your cycle time, the fewer the number of cycles you will go through in any one year. So having long cycle times means that you're going to have fewer cycles at the end of your, when your next plant turnaround is planned to be. We show 3 different bands, good, average, and poor. And what all this does is assumes normal decay. This accounts, the reason for the 3 different curves is it accounts for not only the hydrothermal cycling, but also for typical, and I say typical amounts of contaminants that are in with the feed gas. You can have a decay curve that looks like this, which is non-typical and will result because you may have a lot of liquid carryover because you do not have a properly performing inlet filter coalescer, and your molecular sieves are going to degrade a lot faster when you have a lot of contaminants coming into the system. A lower life factor means that you're going to need more molecular sieves. You remember before, when we looked at the isotherms, we said you had an equilibrium capacity of 23.5 weight percent. And then we modified that by adding a residual loading, and that reduced to 19.5 weight percent. That is only applicable to the equilibrium section. You have to look at the entire, the dynamic capacity, or at the end of life, we sometimes call that useful capacity or breakthrough loading. And when you take into account the aging, the size of the mass, and the size of the mass transfer zone, you're going to go from a theoretical 23.5 weight percent equilibrium capacity to a useful capacity ranging anywhere from 7 to 14 weight percent. What this tells you is you will use molecular sieves because you have to. And you have to use them when you're going for very low water dew points. So the takeaway from this slide, keep contaminants out of the system and try to increase your adsorption cycle time. Okay, let's see what is available on the market today. Commercially, and this is going to be a busy slide because there's a lot of material that I want to make sure that everyone is on board with. You have type 3A. Type 3A has a pore opening, a nominal pore opening of 3 angstroms. It was developed, by the way, for the refining industry to remove water from cracked gas, and over the years has made its way into the natural gas industry because we find use of this material when you want to minimize carbonyl sulfide formation or when methanol was present. Here's the equation for the formation of carbonyl sulfide. If you have H2S in the feed gas together with CO2, it's over an active surface, it's going to form COS and water. And because the sieves love water, it will remove the water from the reaction and force this whole reaction to the right. 3A does not absorb H2S or CO2, so it minimizes this carbonyl sulfide. The water capacity is lower compared to 4A, and it is just not as rugged as type 4A. You need to treat this thing with kid gloves, so you tend to regenerate it at temperatures of about 450 degrees or 232 degrees Celsius. Type 4A, that's the workhorse of the industry. You're going to see this in the majority of natural gas drying applications. You will get more carbonyl sulfide formation. You will absorb H2S on the active sites. It excludes propane and higher hydrocarbons, and you regenerate it generally at higher temperatures. Type 5A finds itself when you're trying to remove trace amounts of H2S and normal mercaptans from the natural gas. It has slightly less water capacity and a slightly lower COS formation compared to type 4A. Because it has a nominal opening of 5 angstroms, this, by the way, has a nominal opening of 4 angstroms, the type 5A will co-absorb propane and higher normal hydrocarbons. And you need to be aware of that if you are using type 5A in, let's say, a turbo expander plant, because the active section of your bed will adsorb propane and higher normal hydrocarbons, and when you bring the unit online, it may create some hiccups in your downstream application. Type 13X, you use that when you want to remove H2S, normal, and isomercaptans from natural gas. It has a higher water capacity than type 4A. The nominal pore opening of 13X is 10 angstroms, not 13, and it promotes carbonyl sulfide formation more than any of the other materials. We generally use 4A material in most of our applications. There are times when you want to go to a 3A. Let's take a look at this chart over here, which shows the molecular diameter, the nominal molecular diameter of some various molecules. And we're going to compare the nominal molecular diameter of some species to what happens on type 3A molecular sieve with a 3 angstrom opening and type 4A molecular sieve with a 4 angstrom opening. Oxygen will not go into 3A, but it will go into 4A. CO2, same deal, because it's 3.3 angstroms versus 3 angstroms. It's not going to get into the 3A, it will into the 4A. Water goes into both. Methanol only into 4A, and H2S is not going to get into the 3A, but it will get into the 4A. This is important. There are a number of units out in the field that have trace amounts of H2S in the feed and are using type 4A to dehydrate. What happens, and you need to be aware of this, what happens is that this shows a water profile. This is the water loaded onto the top of the molecular sieve where you have both water and H2S in the feed. Because the strong components displace the weak and water is much strongly held on compared to H2S, as the water proceeds down the bed, it's going to displace the H2S and force it to roll up. So you get a concentration bump in the active portion of the H2S. This is exacerbated when you regenerate the material, because when you regenerate the material, you're going to get an H2S peak in your spent regeneration gas, which can sometimes be on the order of 50 times what the feed H2S concentration is. Another thing to concern yourself about is that when you empty the material, when you're changing out, you may have H2S loaded on the adsorbent. And in that case, you do not want to wash the adsorbent down with a water wash, because all you're going to end up doing is releasing H2S into the atmosphere. Okay, let's take a look at some cycles. We're going to take a look at a typical 2 and 3 bed cycle. Here's a 2-tower dehydration unit, and we have the cycle chart over here. We're going to take initially a look at adsorbent A, and this is the time shown. And you can see adsorbent A is just in the beginning of its absorption cycle. So we take our wet feed gas, we go through a properly designed and properly operated inlet filter coalescer. We go down through the vessel on adsorption. Because we're at the beginning of the adsorption step, you're only going to load a portion of the water onto the material, onto the sieve. Then you're going to continue to go through a dry gas filter to remove dust, and the gas goes to your downstream processing. Now we're going to take a look at the regeneration. And here, adsorbent B is in regeneration. And the regeneration cycle here consists of the depressurization, the heating, the cooling, and the repressurization. We don't show standby time in here, and I'll explain that in a moment. So we are, in this cycle, we're in, vessel B is in the heating portion of the cycle. So we take a clean regeneration gas, pass it through a heater. You heat the gas up to, if you're using 4A, 550 or so degrees Fahrenheit, 288 degrees Celsius, and you're just getting the bottom of the bed heated up because you're early in the cycle. You go out through a regeneration gas cooler. This regeneration gas cooler needs to be designed for cyclical service because it's going to see temperatures ranging from 100 degrees Fahrenheit up to 500 degrees Fahrenheit. And then the spent regeneration gas gets sent out to wherever your spent regeneration gas is going to go. One of the things to note here is that the regeneration gas that you use is on the order of 5 to 10% of the feed gas. These vessels typically are externally insulated. Here's a 3-vessel system, and we'll look at, you can see that 2 vessels are in a staggered parallel adsorption cycle. Adsorbent A is in the beginning of its adsorption cycle. Let's take a look at adsorbent A. We go through the inlet filter coalescer, through the bed, and we just started the absorption cycle, and we continue out through the product gas. Adsorbent B is in the second step of its adsorption cycle, so it has a lot more water loaded on it, and that's going to look something like that. And the gas is then commingled with the product gas, leaving the first adsorber and out it goes to your downstream system. The regeneration gas is very similar to what we talked about before. Vessel C, here's vessel C, is on its regeneration, its heating cycle. So we go through the heater and up through the vessel that's being heated, and then out, whoops, that was a mistake, out through the regeneration, the spent regeneration gas. So here we're using 3 vessels instead of 2. What determines whether you use 2 or 3 is generally a function of the feed flow rate, pressure drops. In general, CapEx generally rules, and people try to keep the number of vessels down to as few as possible. These things basically, if I can go back just, well, I guess I can. These things really are nothing more than concentrators. You're taking water out of the feed gas, and you're concentrating it in the regeneration gas. So you take maybe, 100 parts of water out of the feed gas, and you concentrate it into the regeneration gas to be maybe 1,000 to 2,000 parts in the regeneration gas. This is another example of a 3-bed system. It shows more definitively the steps. Each block here is called a step time. Vessel A is in the second portion of its absorption cycle. Vessel B over here has just started the reabsorption cycle, and vessel C is in the regeneration cycle. The regeneration cycle consists of the depressurizing, heating, cooling, the repressurizing, and if you listen to me, standby time. I will urge you always, when you have the opportunity, to build in standby time in the regeneration block. It helps you in your troubleshooting. The takeaway for this type of system is that you must finish the entire regeneration cycle before the absorption step time is completed. If you are still regenerating and you have loaded up and your water has progressed down to the end of the bed, that's a whoops. You're going to freeze up your downstream operation, and the only thing you can do in that case is either get more regeneration gas in, use your standby time if you have it, or reduce the water load to your heat. Let's talk about thermal regeneration. Here we have temperature versus hours of cycle, and we show a few different charts over here. This is the red line is the temperature at the outlet of the regeneration gas heater. So as soon as you start your cycle, your temperature pops up to about 288 degrees, 550 degrees Fahrenheit. The green line shows the temperature at the outlet of the bed during regeneration. And you have different sections. First, you have to provide heat to the system. You have to provide sensible heat to the system to heat up the molecular sieves, to heat up the bed support material, to heat up the vessel walls. This is all sensible heat. Then you need to desorb the water. And a good portion of the cycle where the temperature curve tends to flatten out is that portion where you're desorbing the water. The average temperature here looks to be about 125 degrees Celsius or about 250 degrees Fahrenheit, but you can see there's a slope to the desorption. You need to drive the residual water down, so we call that boot, and you need time to continue heating to get the residual water down to an acceptable level. And then finally, you want to cool your vessel to prepare it for the absorption step. You do not want to take a hot regenerated vessel and bring it online because your downstream cold section will not be very happy. So when we look at this, we see that temperature at the outlet of the bed will be roughly 90% of the inlet temperature. Should you end the heating cycle when, let's say, this temperature reaches 500 degrees and your compared to your inlet temperature of 550? The answer is, it depends. As the answer to most of the questions you're going to be asking me at the end of the session. I'll probably say it depends more times than you care to imagine. What does it depend on? Well, it depends primarily on the pressure. If you are regenerating the system at fairly low pressures, and for low pressure, I define that as less than 4,100 kPa or less than 600 PSIA. Excuse me for a moment while I have a little issue here. Here we go. For low pressure regenerations, less than 4,100 kPa or 600 PSIA, you're limited only by the heat that you can put into the system. So the water will be removed from the top of the bed as fast as you can get heat into the system. And in that case, when your outlet temperature here reaches about 500 degrees Fahrenheit, yes, you can end the cycle. On the other hand, if you're regenerating at close to feed pressure, let's say 1,000 kPa or 7,000, excuse me, 1,000 PSIA or 7,000 kPa, then you are going to be limited by the rate at which the water can be swept away. The low pressure is called a heating limited situation. The high pressure is called a rate limited situation. In that case, you're going to have to extend the heating time and have a heat soak on the order of maybe 1 to 2 hours in order to make sure that all the water is stripped away. So in high pressure regeneration, you're going to need to add a heat soak. On low pressure regeneration, you're going to, someone's not muted. On low pressure regeneration, you're going to be able to end it at close to, someone's not muted.
Hey, Harvey?
Yes.
We're trying to figure out where that noise is coming from. That isn't people in the background at your place, the workers?
There's no one here.
Oh, geez. Hey, Clay, can you get Sean and see if he can pop into the session to figure out where this noise is coming from?
Does it sound like a feedback noise or?
No, just if we could ask, everyone appears to be muted, but if everyone could just double check and make sure that your microphone is muted, that would be great. We'll figure it out. Let's keep on
Okay.
going.
So just to finish this up, if we have a low pressure regeneration, ending it when you're about 90% of the inlet temperature, that's fine. High pressure regeneration, you're probably going to need a heat soak because you are stripping limited and not heating limited. Should you build in standby time in the design? Again, we talked a little earlier that this regeneration cycle does not show standby time, but I am a very strong proponent of building in standby time. It will get you out of trouble more times than you care to think about it. Because you have standby time, you can reduce the absorption cycle time. Now that means you're going to have more cycles through the life of the bed, but the increased number of cycles, it does not impact as much as the decay, because the decay curve tends to flatten out. So you want to have standby time when available because it will allow you to reduce your absorption cycle time and still complete the regeneration cycle. Let's take a look at why your dehydrator may not be performing. As I mentioned very early in the session when I showed you that very old black and white picture of a 3-vessel absorption system, these molecular sieve dehydration units have been around for over 50 years, probably closer to 70. So, life of molecular sieves. Why do we change it out? Well, you may not be able to turn the beds around. That means that you may not be able to completely regenerate your vessel before water starts breaking through. That could be due to poor water capacity or not enough time to regenerate the beds. You may not be able to dry the gas to the required specification, and that could be due to leakage or incomplete regeneration or channeling, and we're going to go through all of this. And then finally, a typical reason is that you have a scheduled plant turnaround. We're going to focus just on the first 2 items. So what can go wrong? A lot. Let's take a look at this. I'm going to talk about each one of these items one by one, and they all impact how your absorption unit can function. Let's talk about liquid carryover. This is a problem on a lot of units. The root cause of a lot of operating units issues are due to liquids carrying over into the system. Here we go again. You must have a properly sized and properly operated inlet filter coalescer immediately upstream of the molecular sieve unit. You've got to get the liquids out before they get in the system. Once they're in the system, they're there and they create nothing but issues. The high molecular weight liquid, think oil, is going to coat the molecular sieve particles, and it's going to impede the mass transfer from the gas phase into the solid phase. You're going to end up with a larger mass transfer zone. Liquids such as amines, glycols, salt water, they can have a really bad effect on the molecular sieves and cause actual caking to occur on the vessel, which at times need to be jackhammered out. Keep your liquids out of the system. Some people have asked me in my consulting business, which I get involved with this a lot, should you add a layer of silica gel on the top of the bed? There's been mixed reviews about this. Some people swear by it. Other people say it's just not worth the additional cost. Silica gel has a limited capacity for liquids, and it could saturate very quickly. The silica gel, particularly as the feed temperature increases, loses capacity fairly quickly. The good news, it may work. And if you're going to use silica gel as a protective layer, make sure whatever you get is liquid water stable. On the negative side of the ledger is that you might end up having 2 different vendors, one vendor for the silica gel, another for the molecular sieve, and if you have a warranty claim, they may both point their fingers at each other. Also, some of the silica gel will replace the molecular sieve, which has a higher dynamic water capacity than silica gel. Here's the next, I'm going to say it again. A properly designed and operated filter separator is the best solution. It is better than the Band-Aids that we often talk about. Channeling. You have 2 different types of channeling that occur in the industry. You have flow channeling and absorption channeling, and I'll mention a little about both. You need to have uniform gas flow distribution through the bed. Poor gas flow distribution will result in flow channeling. Imagine some of the gas preferentially going in the middle of the bed and not at the end of the bed. So the gas that flows through the middle of the bed will exit and saturate that portion of the sieve very quickly, and you're going to end up getting wet gas leaking into the product. Baffle plates and distribution headers have proven very successful in the industry. Liquid carryover, what happens is the small amounts of liquid, they'll hit the baffle plate, they run out to the walls because the density of the liquid is much heavier than, or much larger than the density of the gas. So these heavy hydrocarbons run down the vessel wall and they coat the particles. And when you heat it up during regeneration, you're going to crack the hydrocarbon liquids, and it's going to form a carbonaceous material around the pellets or beads that are kissing the vessel wall, and you're going to have very poor mass transfer. This results in adsorption channeling. Your flow distribution can be perfect, but the gas that is flowing near the walls of the adsorption unit will not have all its water removed because the molecular sieve near the walls of the unit are coated with carbonaceous material, and you're going to end up with a slow, steady leak of water in your outlet. Excessive liquid carryover can create caking of the molecular sieve. Some of you may have seen these as donuts, and some of you may have had the experience of having to get in with jackhammers to have to remove it. Changing feed conditions, temperature increases, pressure increases, flow rate increases. It all means you're going to have more water going into the system that may not have been designed for this increased water load. You also have to be concerned about changes in feed or regeneration gas composition. That sometimes you get oxygen, you get hydrogen sulfide, where you didn't plan for it. You get methanol, and you have 4A, and you didn't plan for it. These things can adversely affect the operation of your unit. Contaminants. We talked a little about the contaminants. We said that the hydrocarbon carryover, they're going to crack. Liquid glycol carryover, it's similar to heavy hydrocarbon carryover. Amines, that's a bad thing. You have a lot of amines coming in, and what will happen is that the ammonia formed during the regeneration is going to destroy your binder system, and you're going to end up with expensive dirt in the vessel. You're going to get big chunks that kind of look like this, and that's going to impede the operation of your system. Salt water, that's going to block the macropores, and you can also end up with big chunks. Oxygen, if you have oxygen in the feed, then you really should let your vendor know. We can deal with oxygen in the feed, but if there are different ways to do that, and if it's only oxygen, a small amount probably won't hurt. A little bit larger amount, you may have to regenerate at slightly lower temperatures if you're dealing with a type 4A molecular sieve. H2S and sulfur compounds, we talked a little about this in that you have to be concerned about the H2S roll-up and the fact that water will displace H2S, and you may get a peak in your regeneration gas. And methanol. Methanol will cause a cracking or a coking up of the material, particularly on 4A, if it is heated up to 550 degrees Fahrenheit. So you need to be aware of methanol coming into your feed. Regeneration issues. We have a lot of issues on regeneration. Poor flow distribution is a big one. You want to make sure that you have greater than a 0.01 psi per foot or 0.23 kPa per meter. You need to have good flow distribution in order to properly regenerate the bed. Sometimes you're going to see compound beds of, I'll just use pellets as an example, of 1/8 inch material on the top and a 1/16 of an inch material on a bottom section of the bed. This is used sometimes in order to achieve better flow distribution when your regeneration gas is low. You don't want too much flow, because if you do, you're going to lift the beds. And if you lift the beds, you're probably going to crater or destroy your bed support system. So you want to keep your regeneration flow under the range shown on the slide. Poor vessel insulation. You have poor vessel insulation, the walls are never going to get completely hot, and the molecular sieves near the walls are not going to be fully regenerated. If you have very high pressure, large diameter, externally insulated vessels, you need to be aware of the wall effects of the thick steel. It could take more gas, more regeneration gas than you think to properly regenerate. With very large vessels, you might want to consider an internal insulation. Other regeneration issues, maybe your temperature, you don't have your regeneration gas hot enough. Maybe you're only 350 degrees Fahrenheit and you just don't have enough time to regenerate a vessel at such a low temperature. Maybe you don't have enough regeneration gas flow. Maybe your regeneration gas is wet. And if it's wet due to mechanical issues and you're regenerating countercurrent to absorption, you're going to lay down water at the product outlet of the bed. And finally, on this slide, you could have something that is seen in high pressure operations called regeneration reflux. In regeneration reflux with high pressure gas, what happens is because the pressure is so high, the water that is being released from the adsorbent is not swept away, and instead it ends up condensing on the cooler vessel walls and creates a rolling boil on the top of the bed. And this rolling boil, especially when you get a little bit of amine carryover, tends to wash the binder away, and you end up with a hard baked donut-shaped cake, which is not good for your system. Mechanical issues. There are a host of mechanical issues that you need to be aware of. The switching valves can get stuck. You can have valves leaking because someone didn't put in the proper gaskets. Maybe they're not switching on time. There's a host of valve issues that you need to be aware of. Maybe you have heat exchanger leaks. One of the areas to consider, particularly for environmental situations, is that spent regen gas cooler, because it undergoes a temperature swing, and you need to be aware of the design to accommodate that temperature swing. If you're using steam as a heating medium, you need to be careful of steam leaks into the clean regeneration gas, because all of a sudden your regeneration gas is not going to be dry, it's going to be wet. You may have, bed support failure. You may have bed support failure. A typical bed support failure is shown over here. This is a beam type arrangement where we take wide flange beams and we build a bed support system on top of the beams. These beams need to be designed in order to expand. Remember, you have a large temperature swing going on in this steel vessel. To give you an idea of the expansion, an 8-foot, 2.4 meter diameter vessel will expand by about 1/3 of an inch, that's about 8 millimeters, when heated from the adsorption temperature to the heating temperature. If these wide flange beams are welded to the vessel wall, as I have seen them being done, they're going to end up buckling. And when they buckle, the whole support system is going to fail, and you're going to get your adsorbent loading out or filling out the bottom head, and your adsorbent system is not going to be working properly. So a properly designed bed support system is important. The beds may not switch as you desire. The switching sequence can be out of sequence, and you're going to have to consider that. Analytical issues. You have to be aware of analytical issues. Check your analyzers. Check your thermocouples. Check your gauges. Just don't take the reading and think that that's the way it has to be. Make sure they're functioning properly. And finally, on analyzers, make sure your water analyzer can differentiate between methanol and water. Some analyzers think methanol is water because of the polar nature of the methanol. And some facilities have reported that when methanol is injected upstream, they see an increase in water downstream of their dehydrators, and that's because their water analyzer is measuring the methanol and reports it as water. But what can you do? What you can do is you can run performance test units periodically. I'm going to interrupt this just briefly to show this slide over here. By running if you run performance test units on a frequent basis, let's say you run it at 500 cycles and you can plot where you are on a performance test run, and then you run another cycle, let's say at 1,000, and you have a pretty good idea of what your decay curve is going to look like, and consequently, you're going to have a pretty good idea of when you can change out your adsorbent. So running frequent performance tests is a very good idea. And there are times, and in fact, if you look at the PetroSkills tip of the month, there are issues where there's a tip of the month that shows how you can determine the life of the sieve by running just one performance test run. Why you can run as many as you possibly can. Keep good records. Keep records of the changes in feed and regeneration gas rates, and the compositions, changes in compositions, pressures, changes in temperatures. When you report this to your vendor, he's going to want to have all of this information. Record any unusual events, such as liquid carryover, sudden depressurization, amine burping into your unit. Your vendor's going to want to know about this. Try to have standby time built into the unit. I've said it numerous times. That should be a key learning point for you. Standby time is good. And know the design margin of your regeneration circuit. If you have the 10% design margin in your regeneration circuit, that can translate to extra standby time. And confirm that your regeneration gas is clean and dry. Make sure that you're using the proper gas to regenerate. Otherwise, you'll never achieve the adsorption performance that you're looking for. That covers what we wanted to discuss today in this webinar. We talked about how an adsorbent works. We described the various types of molecular sieves available, 3A, 4A, which is the workhorse of the industry, 5A and 13X. We talked about and showed a typical dehydration, adsorption, and regeneration cycle for both a 2-bed system and a 3-bed system. And we just ended the session by highlighting various things that could go wrong and cause your dehydrator performance to not meet specification. With that, I'm going to turn this over to who? Who gets this? Am I talking to myself?
I am so sorry. Hold on. All right, am I unmuted? I'm sorry. I was.
There you go. All good.
All right, everyone. So before we end and go into our question and answer session, what I would like to do is I want us to take our quiz. And so if you just give me a moment so I can start sharing my screen. All right. So before we go and take our quiz, I just want to say thank you, everyone, for joining us today. And I would like to thank Harvey. Harvey, thank you for the excellent presentation on molecular sieve. And everyone who's on the call, I would like to just quickly apologize for the background noise. I'm not sure if something happened. We weren't able to mute those who had dialed in on their phones. So thank you for being understanding. If you guys are interested in learning more about molecular sieve, we have a number of different instructor-led and virtual courses. So our G4 gas conditioning and processing course. We also have operator training options as well as various online modules. As far as the quiz, here's your cheat sheet, all right? And so basically this quiz is for fun. And so if you could get your cell phone out, or for those of you who have dialed in on your computer, you can play it on your computer. So what I need you to do is open up a web browser and type kahoot.it, all right? And then you'll be looking at my presentation for the PIN number. You put your PIN in, you can put your name in, you could be anyone you want today, or you could use your real name. And then you'll answer the questions via your phone, so you'll see them on the screen. And so be quick because your time is limited. And so let's have a look. Here we go. And I'm going to play. All right, so the PIN number is 634484. Nicole Lester King. That's a great name. All right, I'm going to go ahead and start the game. The PIN number will still show, and so it's 634484. You'll have a chance to join in if you have not already. So here we go. All right, excellent work. The 4A molecular sieve is the workhorse in the industry because Harvey mentioned that it is by far the most robust, or the strongest type of sieve that we have available to us. So it should have a longer life as compared to a 3A, which is a bit more delicate. All right, so it looks like Jeep is in the lead, followed by Leandro. All right, so that's a typical application for molecular sieves. All right, so a typical application for molecular sieves for water removal is cryogenic processing only. And the reason why is because molecular sieves are so incredibly inefficient in removing water. Because remember, Harvey said generally we get 7 to 14 pounds or kilograms of water removed for every 100 pounds or kilograms of molecular sieve. And then we have to heat up our inlet gas rate, say maybe, I don't know, 5 to 10% of our inlet gas up to extremely hot temperatures. And so it's very expensive. It's expensive to install. It's expensive to operate. And so if I was going to do gas pipeline dehydration, generally that's TEG because it's very efficient and it's also very capital cost and operating cost very minimal. If I'm going into a propane refrigeration unit, generally that's going to be hydrate inhibition with MEG. So let's have a look. All right, so Jeep is in the lead, followed by Trini Man. All right, nice job. So here's the deal. CO2 can only absorb onto a molecular sieve that has a pore opening that's large enough to accept it. And so CO2 can go into a 4A sieve. It's too large to fit into a 3A sieve. And so part of your molecular sieve selection really depends on what's in your gas and what are you trying to achieve in your unit. So nice work, everyone. Srinivas is now in the lead, followed by ZS. All right, excellent job. So here's the deal. Molecular sieve will be very adversely affected by liquid carryover. And so Harvey spent a fair amount of time talking about the adverse effects of, what happens when you send a chunk of amine or, a gallon of amine into your system. As far as regenerating with product gas, that we can do it, it's fine, and we can operate. It doesn't hurt the sieve at all. If we're regenerating at lower pressure, just remember you got to be really careful when you pressure up the bed and depressure the bed that you don't do it too quickly to, cause that bed a bump, so you don't destroy, have any mechanical issues with it. So as far as this quiz question, it was liquid carryover. And ZS is now in the lead, followed by Jeep. All right, excellent job. So channeling occurs when I get liquid carryover coating my adsorbent. It will coke and then impede my mass transfer. So that is a bad deal. And ZS is still in the lead, followed by Jeep. All right, beautiful job. Typically, my total regeneration time is less than or equal to the adsorption time. If it's greater than my adsorption time, that's a problem because now I won't be able to get my beds regenerated before it's time to switch them to another bed. So that means I'm operating under water breakthrough, and probably my cryogenic plant downstream is going to be freezing off. So that's a bad deal. So we always have to have it regenerated before my adsorption cycle is done. All right, ZS is in the lead, followed by G. All right, excellent job. So critical factors to consider: you have to be sure you have a really good inlet separation. So an adequately sized inlet filter coalescer or coalescing filter. You would like to have excess capacity in your regeneration system, including that standby time, because as Harvey mentioned, that's going to give you a lot of operational flexibility. In addition, you should always be maintaining your records on your process changes and record any unusual events. So nice job. All right, excellent. So this webinar, I'm glad you guys got a lot of excellent information out of it. I really appreciate you all dialing in. And so let's see who the first place winner was of the quiz. All right, DS took the lead. Excellent job. All right, so with that said, let's go into our question and answers. So Clay, how are we doing on time? And is my audio coming through okay still? Do I sound all right?
Yep, we can hear you great. We're just now getting up to an hour and a half, so we got quite a few questions here. So I think probably the best thing to do, Kendra, if you want to select a few of the questions that you and Harvey can address, and then whatever we don't have time for, we will answer in a post that we'll put on the site for this page, and then we'll send it out to everybody afterwards. So we'll get to all the questions, but if you want to select a few to highlight now, then we can use the last 5 or 10 minutes doing that.
Sure, that sounds excellent. So the first one, this is a good question, Harvey. Someone would like to ask about changing an original project which was originally designed for 4A sieve. And so they want to know, what are the important variables to consider when you evaluate doing that change out besides the thermal demand or the temperature? Is there anything else that they need to be aware of or check?
They want to change out the 4A sieve to a different sieve?
Yeah, to a 3A.
You want to change out from 4A to 3A.
Yes.
Yeah, there's a lot of stuff to be concerned about. For the first, the water capacity of type 3A is less than the water capacity, the equilibrium water capacity of type 4A. The second thing you need to be concerned about is the mass transfer zone of type 3A is going to be significantly larger than the mass transfer zone of type 4A. And finally, you want to make sure you do not regenerate the type 3A at temperatures in excess of 450 degrees Fahrenheit, that's 232 degrees Celsius. Those are the three things that immediately occurred to me if you're changing from a 4A to a type 3A.
So Harvey, I guess one of the things that I've seen as far as the reasons why people have been moving this direction is because the issue with methanol contamination on the 4A sieve. And
yes.
so when you think about that, and you think about, what was happening with the 4A sieve beds and that, if they were having reduced bed life as a result of the methanol messing up their mass transfer zone, do you think then it's reasonable? Or I guess, because I kind of wonder, do they have to change the regeneration times to account for the fact that it has less water handling capacity? I mean, is that something else that they need to look at? Or is it that once we remove the methanol issue that, maybe we're going to get the same bed life that we had as the 4A did or was experiencing?
Well, those are good comments because you are correct. Because the 3A has lower water capacity, you're going to need to turn the beds around quicker.
Okay.
So you're going to need more regeneration time. You might have to revamp your regeneration circuit. What I would try before doing a change out is I would try to regenerate the vessels with 4A at 450 degrees Fahrenheit and see if that made any difference, if that increased the if that improved the outlet dew point spec as opposed to regenerating at 550. I would tend to try that if I already had the 4A in the system.
Excellent. That's a good recommendation. Thank you for that, Harvey. I got an easy one here. So because I'm going to try to cover more than just a couple. What is acid resistant 4A? What is that?
I have no idea.
Oh, no.
I don't know what acid resistant 4A is. I will say this, that the vendors, the major vendors, all zeolites or molecular sieves are made of zeolite crystals, which is like a powder. And what they do is they form it into either a bead or a pellet by using a binder system. And the binder system is essentially an amorphous clay, and that's what gives it its shape. And the vendors keep the binder system that they use fairly secret. They don't want that getting to their competitors. Some binders are more resistant to liquid carryover than other binders. I haven't heard an acid-resistant type 4A, but there are naturally occurring zeolites, mordanite and cabazite, which are highly acid resistant and do a good job in removing water from natural gas when you have a lot of sour gas. The problem with those units, with that material, is the water capacity and the mass transfer zone is considerably larger than the type 4A. That's a general answer.
Okay, thank you. All right, how about another question? When you're running your breakthrough tests, is it possible to run with the chilled mirror method, so the Bureau Mines method? Or what analyzer do you recommend? And they're asking this because of the response time of Panametrics and Amatec products are different, for example.
Yeah.
When you're looking at, go ahead.
I have not seen or done a chilled mirror test on the outlet of a dehydrator. I don't know if a chilled mirror is going to work at less than 1/10 of a part per million by volume. I understand about the response times. I thought Amatec had a fairly robust response time, but I could be wrong. But depending on the situation, if you have a turbo expander, then running a a breakthrough test at the outlet of the bed is not going to get you into trouble, because you could always squirt a little bit of methanol in if you find that your turbo expander pressure drop is starting to freeze up. The other thing you could do, if you have the opportunity, is have internal bed probes where you run moisture breakthrough both to the probe on the that's extending into maybe a third of the way into the bed, as well as the another probe at the outlet of the bed.
All right, Clay, do we have time for one more question, or shall we drop off?
Yeah, let's hit one more, and then again, anything we don't get to, we will address and send out to everybody.
Okay, excellent. So, Harvey, the next question is going to be in regards to regeneration. And so when you're doing regeneration, do you recommend a heat ramp to the desired temperature, or would you rather have two steps to allow the bed and the molecular sieve to heat up? And so what is the risk of doing direct heat ramp as compared to two stepwise heating?
Good points. Good question. So it's a heat ramp versus heat and cool is, as I understand the question. And of course the answer is it depends. The heat ramp is used, when we talked about in the presentation, the high pressure regeneration creating a regeneration reflux. One way to get away from that reflux situation is to ramp heat. And adding a ramp heat when you have high pressure regeneration, I think, is a good tool to use. The issue with that is that it's going to extend the regeneration time that you need. Generally, when you ramp heat, when I like to ramp heat, I try to increase the temperature from 1 to 1.5 to 3 degrees Celsius. That's about 3 to 5 degrees Fahrenheit per minute. And I'll start out at about maybe 65 degrees Celsius. That's about 120 or so degrees Fahrenheit. And I'll ramp heat the whole thing up at that rate up to the final temperature. It's going to add an hour or two to the regeneration cycle, but there are times when ramp heating is definitely the type of cycle that you want to do. On low pressure regenerations, I wouldn't bother. I would just heat and cool.
Excellent. Thank you so much. So everyone, I'll pass this back over to Clay. Please check the website. We will be posting detailed answers to all of the questions that you have submitted. And so I apologize if we didn't get to your specific question, but give us, I don't know, a day or two, and those will be posted, and Clay will advise when those are available. And so, Clay, would you like to close out the session?
Yeah, thank you, Kendra, for running the show here. Harvey, thank you so much for the awesome presentation, and thanks to everyone who joined us. We'll get all this information out to you in the next couple days. Thanks for spending your time with us this morning, this afternoon, or this evening, depending on where you are. And we hope to see you again soon in the next coming weeks. Thanks, everybody.
Hey, Clay, one thing to mention really quickly. For those of you who didn't get their questions answered, if you go to Harvey's his website, www.exactdifferentials.com, he has an awesome blog where a number of those questions have already been answered. So I encourage you to go there and check it out and take a look at Harvey's blog, because that will definitely find some good information there. So thank you, everyone, and thank you, Clay, for putting this together.
You bet, and I'll include that URL to Harvey's blog with the materials as well. That's a good point.
Okay, excellent. Thank you so much.
Okay,
I would like to thank everyone too for staying with us.
Absolutely. All right, be safe, everybody, and take care.
Bye.
Bye-bye.